Thanks everyone for coming. Welcome to the special public lecture put on by the Department of Physics and Astronomy here. It's good to see so many people here excited about the very, very recent and very big news from just less than 2 weeks ago, right? This is the biggest, in my mind, the biggest physics news in a decade or more, for sure. And it's not just that we saw something, detected it for the first time that Einstein predicted 100 years ago. It's that it's almost like we have a new sense on the universe, right? We can find out what's going on in the universe like we've just developed a sixth sense. And so we're not seeing things with electromagnetic radiation, we're experiencing them by looking at the ripples in space-time itself. And maybe even beyond that, we maybe take a really big picture view. I mean, this is something that people work on for decades and decades. Really hard problem. A lot of people work together, and it worked, and it all came together. And I don't know, this kind of gives me hope for other big problems that we face. You know, humanity can do amazing things. Okay, so their speakers today are two members of the physics department. We have Peter Beiersdorf here on my left, and Aaron Romanowski on my right. Peter is our department's inside man in LIGO. The LIGO, you'll keep hearing this acronym, it's the collaboration that announced these results. He began working on interferometry for gravitational wave detection in 1996 as a PhD student at Stanford. He spent 4 years in Japan as a scientist at a gravitational wave detector there, and established SDSU as a member of the LIGO science collaboration when he came to SDSU in 2006. He sent 2 graduate students to work at the LIGO detector up in Washington, and he's remained active in developing instrumentation for advanced LIGO through 2013. Aaron is our department's newest astrophysicist. He studied UC Santa Barbara and Harvard, held postdocs in various countries, started as faculty here in 2012. He works mainly on galaxy formation and dark matter, but also dabbles in searches for black holes, which we'll be talking about. In fact, one of his undergraduate students discovered an unusual black hole candidate that's being followed up on with the Hubble Space Telescope. And just today, we learned that Aaron is one of 24 national recipients of the Cottrell Scholar, and the only CSU scientist on the list, a very impressive and prestigious honor. So Peter will speak first, and then Aaron. Let's try to hold our questions, and I'm sure there'll be lots of them to the end. So write them down if you're worried you'll forget them. And after we've heard from both of our speakers, I'm sure they'll be happy to answer your questions. So without further ado, Peter Barr.
Thank you, Ken. So I did want to acknowledge that although this is big science and a huge collaboration that involves cross-disciplinary and cross-institution work, there were students here at San Jose State that contributed to this work. That's not a student, that's me testing out some optics in a prototype. That's Adnan Alan, who is a student of mine who went to LIGO to man the detector for a couple weeks during the initial LIGO science run. And Mark Cordier at the Gravitational Wave Advanced Detector workshop. He also spent some time at LIGO, but all he took was beautiful pictures of the sky, so I had nothing to show from that. Look deep into nature, and then you'll understand everything better. That's what LIGO set out to do, look deep into nature. In order to describe what LIGO saw, I want to start with what is gravity, so we can understand gravitational waves, how they're detected, and why this is such a difficult measurement to make. So the version of gravity that most of us are familiar with, that we still teach at the undergraduate, even at the graduate level, is Newtonian gravity, which is summarized by this equation up here. There's not very many equations in this talk, and we're not going to go into too much detail, but you may recognize this from a previous class. And the Newtonian theory of gravity works pretty well for understanding the basic motion of things, and it mostly describes the motion of the planets. There's a little bit of an anomaly with the way that Mercury's orbit behaves when modeled with Newtonian gravity. And this bothered a number of people at the turn of the century, the turn of the previous century. And Einstein, in 1905, published his special theory of relativity. And with the understanding that nothing travels faster than the speed of light, this equation for gravity has a particularly troubling consequence. It seems to say that if you were to somehow change the mass, say m1 in that equation, let's say it was the sun and it went supernova and its mass suddenly changed, this seems to suggest that other objects that are feeling the influence of the sun's gravity should instantaneously feel a change. And that doesn't agree with the special theory of relativity that says information takes time to propagate. It can't propagate faster than the speed of light. So enter Einstein. He comes up with an alternative theory of gravity, a very elegant theory called the general theory of relativity. There's an equation down here that very few of you probably recognize at all, but it's relating the stress in space to a strain. It's essentially Hooke's law. And the stress is caused by mass. So you can imagine, for example, the Earth here being a large mass, causing a strain in the space-time around it. And we typically represent that with some sort of warped mesh drawn underneath our massive object. And so that's what's shown here. And the reason that that works to describe gravity is because then you can imagine what the influence of that warped space is on objects traveling through it. So for example, Earth warps space-time. The moon is in the vicinity of that warped space-time, and so when it travels, it follows a geodesic, the shortest path along this curved surface. And the shortest path along a curved surface is not a straight line. Turns out, in this particular case, it will be an elliptical orbit around the Earth. Think of it as if you were to roll a ball in a bowl shaped like that. You'd expect it to roll in sort of a circular path, and that's the premise of Einstein's theory of general relativity. So this theory not only describes space and time as the conduit for gravitational interaction, it also has predictive power. So for example, one of the most massive objects near us is the sun. And so if objects are warped when they travel in a distorted path, when they pass through a warped space-time, we would expect that things passing through the warped space-time near the sun should travel in a curved path. And in this theory of general relativity, it doesn't matter what that thing is. It doesn't have to be a massive object. It can even be light. And so the prediction is that light should also travel a curved path in warped space-time. And so people were interested in testing if this were true. I mean, you can imagine looking just past the sun at a star and seeing if its apparent position had shifted from where you expect it to be when the sun was not in between you and the star. Of course, the problem with doing this is you're not supposed to look at the sun, and the background light would just drown out any starlight, so you have to wait for an eclipse. This is exactly what people did. Einstein's general theory of relativity was published in 1915, 101 years ago this year. People waited until 1929, when there was an eclipse, to be able to test Einstein's theory observationally. And what they found was that the exact shift in the apparent position of the stars behind the sun manifested itself in their observations. It was one of the first observational tests of Einstein's theory of relativity. The following year, after Einstein proposed this theory, in 1916, he was looking at the equations and realized that if gravity causes a warping of space-time, then changes in a mass distribution should result in a changing warping that would propagate outwards at the speed of light. He called those gravitational waves. Okay, so 100 years ago this year, gravitational waves were first theorized. However, this is a quote from his paper in 1916. It's obvious that the amplitude of gravitational waves has, in all imaginable cases, a practically vanishing value. Einstein did not believe it was possible to ever observe these gravitational waves that his theory predicted. They were just an intellectual curiosity. Now, in order to put ourselves in Einstein's mind, it's a big mind to fill, but we can try to imagine what he might have been thinking when he came up with this statement. Electromagnetic waves had just been proved 50 or so years earlier, and it was the Frank Hertz experiment that did that. And this experiment basically created an electromagnetic wave by introducing a spark between two high voltage conductors. And then the electromagnetic waves produced by that spark would propagate outwards, and an antenna would pick them up. And so This instrument over here produced a spark in this gap, and then this detector over here would show an identical spark at the same time, proving that the spark had produced waves that had propagated through. Okay? So you can ask, could you do this Hertz experiment with gravitational waves? So you might think of starting with some large mass that's rapidly accelerating, which is the criteria for generating gravitational waves. So imagine something like a barbell, 200-pound barbell, and spin it at the speed that like a car engine or a steam engine could spin something, 6,000 RPMs, and ask, what is the magnitude? What is the maximum magnitude of the strain induced by gravitational waves? We'll see in a few minutes what that means. And when you calculate this out, if you get as close to that spinning barbell as you possibly can and measure the strain, you get a value that's a 0 followed by 41 more zeros, 10 to the minus 42. Okay, so impossibly small. But, you know, we live in a modern time. We have things fancier than barbells and car motors. Let's imagine we take two fighter jets. These are very massive. And let's attach them to the ends of a rotor and have them go Mach 1. That sounds pretty good, right? So we've got a huge mass distribution, accelerating very rapidly, and we calculate the strain we'd expect to get if we could get as close as possible to those fighter jets. And we get something like 10 to the minus 36 in strain. Okay, so you'd be measuring, say, a meter stick changing by 1 part in 10 to the 36. Right? That's hopeless. But it turns out we don't have to create this experiment. Nature has its own experiments going on all around us. We can look to binary star systems. We know these exist, and these are hugely massive objects. And if they're emitting gravitational waves as they rotate around each other, even if those waves are indetectable to us because they're so small, they should be losing energy. And as they're losing energy, their orbital radius should decrease. And eventually, they should be moving very fast due to conservation of angular momentum, just like a figure skater pulls her arms in and moves much faster. As their orbital radius decreases, we'd expect these things to speed up and eventually potentially give strain signals that could be as large as 10 to the minus 21 if measured from Earth to some solar mass binary system somewhere in our galaxy. So this still seems incredibly impossible, really. But there was hope. In the 1970s, two astronomers, Joseph Taylor and Russell Hulse, were using the Arecibo telescope and looking for pulsars. These are rapidly rotating neutron stars that spit out a pulse of electromagnetic radiation at regular intervals. Every time they rotate by, they're like a beacon or a lighthouse flashing a light that we can use to measure very accurately the timing of their rotation. And we can use the redshift to measure the timing of the orbits of this binary star system. And this is exactly the kind of system that might emit gravitational waves. And so they measured the period of orbit. And then they did the same thing the next year, and the next year. And for their entire career, they monitored the orbits. And what they got is data that followed exactly the line predicted by the energy that should be lost due to radiating gravitational waves. And you can see, this took 30 years. This was their entire career. But it was worth it. They got the Nobel Prize. So what other astrophysical sources might there be that could produce observable gravitational waves? And is there a way to detect them that's more direct than simply noticing the fact that they're carrying away energy from things? Can we directly observe them? So there are a variety of sources. There are things like the microwave background radiation, right? The 2.7 Kelvin background radiation that's left over from the Big Bang. Any gravitational radiation in the universe at that point should have encoded itself on that background. And so it should be possible to look at the polarization of the light in that background and infer the presence of gravitational radiation. That's a very slowly changing event. In fact, the gravitational waves emitted by that cosmic microwave background would have only oscillated by about 100 cycles during the length of the entire universe. So that's a very low frequency events. At higher frequency, we start to see things potentially like supermassive binaries. So I mentioned binary systems of solar masses, but as the mass of the system increases, we know that there's million, almost billion solar mass black holes. If we can imagine binary systems that have very large mass, they should orbit very slowly and produce very large amplitude gravitational waves. And we see that by the fact that on the horizontal axis here we have frequency. So this is a frequency of about once per year. And the amplitude here is a strain, the size of the signal we'd expect to be able to detect. And as you see, as we go to higher and higher frequencies, the signals become lower and lower, making it harder to detect. But it turns out on Earth, we really can't measure gravitational waves directly at these very low frequencies, because they involve measuring changes in length very slowly over the course of years. And we live on an Earth that's rapidly rotating, that has ground motion, that has all sorts of things that don't allow us to have a detector that's stationary over the course of years. To do that, you really need to go out into space. Right? So you could time pulsars to observe things like this, like Hulse Taylor did. There's a space-based interferometer that's been proposed to measure things like this. But when you get down here to the audio frequency, 100 hertz, right? That's frequencies at which, 10 milliseconds, we can build things that stay stationary for 10 milliseconds. That's not hard. So we might expect to see things like neutron-star binary systems that coalesce. Coalesce means collide with each other as their orbital radius decreases to the point that they merge. Black hole binary systems have also been theorized to exist, and if they did, they should give off gravitational radiation when they merge as well. And we can ask, what type of a waveform would they produce? What would that gravitational wave signal look like? And so up here is a calculated waveform that shows the strain oscillating back and forth and the frequency increasing as well as the amplitude in what we like to call a chirp. Because if we were to play this is an audio frequency, remember. If we were to play this, take this waveform and pump it through speakers, we would hear what sounded sort of like a bird's chirp. So let's do that. That's the predicted waveform for a neutron-star in spiral. Okay, so how could we measure this? Imagine for a moment you have a ring. So this could be a hula hoop. This could be a series of point masses you place in a circle. And for the moment, let's just put these out in outer space. They're in free fall under the influence of no forces other than gravity. Now let's imagine a gravitational wave is passing directly through this ring along a line that's perpendicular to the plane of the screen. That passing gravitational wave will produce a strain. It will stretch or compress space-time. And in fact, it will do it in a very particular way. We see here that it's stretching along one dimension at the same time that it's squishing in the orthogonal dimension. And those strains oscillate back and forth. Okay, so now instead of having a single ring, let's spread those rings out and imagine what a passing gravitational wave would look like. Okay, so this is how you could visualize a gravitational wave passing through a tube of circles. If you want to visualize it passing through the Earth, you might see something like this. Now, don't be alarmed. This effect is vastly exaggerated. So this is a chirped waveform. You saw the amplitude and frequency increase and then suddenly stop and decay. So why search for gravitational waves? I mean, Einstein's theory predicted them, but so what? Well, imagine you're an explorer. Maybe you're a biologist or an ecologist, and you go out and you want to study in the field. Your domain of observation is the forest. If you're an astronomer, your domain of observation is the heavens. You can learn a lot by going and looking at this forest, right? You can see vegetation here. You might be able to see a bird or two if you have sharp eyes, but there's a lot you cannot see, right? There are things hidden behind the tree that you will never see. There are things that are too small to be seen. They're not scattering enough light. They're not subtending a large enough angle. They're just invisible to you. You don't have the right sense to observe this. But what if you also had your ears? You get a totally different picture. There's so much more information there. And this is an analogy to studying gravitational waves and observing the signals that come from the universe with a completely different medium. In the 1600s, Galileo used a telescope for the first time to look at the stars. The field of observational astronomy has not been the same since. There was the single biggest leap forward in astronomical observation. That changed last year. Or at least, if not a bigger event, an event on par to this. There is now a new way to observe the universe that doesn't involve light at all. So back to our gravitational waves. How can they be detected? Lots of people have had different ideas about this. Joseph Weber was the first to seriously try to detect gravitational waves. He was a professor at the University of Maryland, and he had the idea that you could take these large metal bars, shown here, and you could cool them down to cryogenic temperatures. So they had very little thermal energy, and they would essentially be stationary, just these very still bars. And physically they are bars, but in practice really what they were bells. Because if you hit them, they would ring at a very specific frequency defined by their geometry. And the geometry was chosen such that the frequencies at which they would ring corresponded to the middle of what we thought was the detectable gravitational wave band, where there ought to be gravitational waves that could potentially excite and ring up these bars. And using these superconducting quantum interference devices to read out the motion of the bars, he hoped to be able to detect, in a very narrow bandwidth, the presence of gravitational waves. There's not a lot of observation you could do with this. You might be able to see a wave, but you wouldn't see its frequency spectrum. You wouldn't see its full waveform. You'd just see its presence identified by the ringing of the bar. So there were a few times where he thought he had seen something, but ultimately was never able to get the sensitivity low enough to be able to confirm an observation. In the 1970s, another scientist, this one at MIT, Ray Weiss, had another idea for how you could detect gravitational waves. You could use a Michelson interferometer, we'll describe that in a little more detail in a minute, as a probe of the differential strain of space-time. This is the same interferometer that Michelson and Morley used to prove that the Earth was not traveling through an ether that affected the propagation of light. And he very carefully went through all the possible noise sources that might be present in such an interferometer and described how those might be dealt with to get to a strain sensitivity necessary for detecting gravitational waves. Kip Thorne was a young professor at Caltech. You may know Kip Thorne or not realize it, but if you saw the movie Interstellar, he was the executive producer. He deals with black holes, warped space-time. And he came up with a number of equations and did the theory that laid the groundwork for the expected sources that would be detected by these interferometers, and showed that there's a reasonable chance that there are astrophysical sources that have a magnitude sufficient to be detected by these new devices. And in Glasgow, Ron Drever had read the paper of Ray Weiss and came up with a number of improvements on the basic interferometer design that Ray Weiss had proposed, published those, and then was subsequently recruited by Caltech to join their faculty, so that Ron Drever and Kip Thorne, working at Caltech, in collaboration with Ray Weiss at MIT, could put together a project to actually make this a reality. So they did. That was LIGO. So here's an example of how an interferometer could be used to detect gravitational waves. So this cylinder right here is a representation of a laser. This thin disk represents a beam splitter, and then we have mirrors at either end, and a photodetector to measure the amount of light that comes out of this interferometer is the square here. So the beam splitter splits the light and sends it back towards the laser. And if you arrange this properly, then any motion of the mirrors manifests themselves as a changing output of the interferometer. And that's because light is made up of wavelengths, right? And as the light propagates, it propagates a certain number of wavelengths. And when the electromagnetic fields interfere at the beam splitter, if those waves are out of phase, they will cancel out and you'll get no light out like this. Okay, but if those arms move relative to each other, it changes the relative path length. And as a result, the phase difference between those interfering beams changes, and you go from destructive interference to partially constructive interference. And it changes the light on the detector. So you can read out that light, and if that change is due to a passing gravitational wave, then the information about that gravitational wave is encoded on that light and on the signal that you read out. So, a quote from Kip Thorne in 1973. The technical difficulties to be surmounted in constructing such detectors are enormous, but physicists are ingenious, and with the support of a broad lay public, all obstacles will surely be overcome. So he's prophetic. These detectors eventually got built. This is a detector in Hanford, Washington. It's big. Okay, 4 kilometers on a side. You can see it has the basic shape of that Michelson interferometer I just showed. And because this is the United States, and as I said in Contact, the movie Contact, if you're going to build something, why not build 2? So one was built in Livingston, Louisiana. Now, there's a reason for that, of course. If you see something, you want to be sure that it's astrophysical in nature, and the best way to do that is to have multiple detectors far separated so that there's very little correlation of any instrumental noise. So let's take a look inside these detectors. These are the high vacuum beam tubes, world's largest high vacuum, 10 to the minus 9 torr. They're 1.2 meters in diameter, and each arm is 4 kilometers long, so that makes more than 16,000 cubic meters of ultra-high vacuum. At the end of the arms, we have these mirrors. This may not look like a mirror, but this thing right here is a mirror. It's reflective for infrared light, which LIGO uses a 1 micron laser light. So it's fairly transparent to visible light, and it's surrounded by this cage. That cage is there to protect it in the event of an earthquake or something that would shake it abnormally strongly. And it's suspended by thin wires. Actually, in the current advanced LIGO, it's suspended by glass fibers that are less than a millimeter thick. So you can't even see them in this picture. There's a better shot of one of the mirrors. And there's a shot of one of the optical tables that takes the light from the laser and conditions it for sending into the interferometer. So it's a complex optical setup. So there are 2 of these, one in Hanford, Washington, one in Livingston, Louisiana. And these sites are separated by about 10 milliseconds of light travel time, or 10 milliseconds of gravitational wave travel time, if you like. That turns to be important later on. And with 2 detectors, you can use the arrival time of a signal, if you were to see such a thing, at each detector, to determine an annulus on the sky from which that signal must have come. So imagine these 2 dots represent our detector, then this cyan ring represents an annulus on the sky from which you could assume a signal came based on the timing. If you were to have a different detector somewhere on the Earth, and you had a pair of detectors detecting a signal, you could localize that signal to a different annulus on the sky. So here is the Virgo detector in Italy. This was a French-Italian collaboration, and when it began, it was somewhat of a competitor to LIGO. But both the Virgo collaboration and the LIGO scientific collaboration realized that you really couldn't make a confident detection and do useful observations with a limited set of detectors. You really needed to pool your resources. And so the collaborations joined and became the LIGO-Virgo collaboration. And so now you also have the annulus on the sky found from all the different combinations of these 3 detectors, and that can localize a source to 2 different points. If you had a 4th detector that wasn't co-located with any of these, you could then confidently resolve where in the sky a signal came from. It's exactly the way GPS works. If you have at least 4 satellites, you can figure out where you are. Here, it's the opposite. We have 4 detectors. We're figuring out where the signal source came from. And so combined with the antenna pattern of a gravitational wave detector, depending on the polarization state, whether it's aligned to the arms of the interferometer or whether it's the so-called cross polarization, you have a different detector interference pattern or antenna pattern. And that lets you determine on the sky from just the 2 LIGO detectors. I'm sorry, this is the 2 LIGO detectors plus the Virgo detector. If you were to see a source, this tells you how well you could localize it if it came from various segments of the sky. And what you can see is that there's a sort of triangular path that cuts across this diagram where you have very poor localization. And that's in the plane of the triangle formed by these 3 detectors. Okay, and it's a reason why if you were to build a 4th detector, you might want to try to build it out of plane of that triangle. So these detectors were built, but there are many technical challenges to operating them. So I'll go through those in a little bit of detail now. The first is seismic motion. We build these on the ground, and the ground is moving. The seismic motion of the ground, depending on where you are, is about 10 to the minus 6 meters, about a micron of RMS displacement. Not RMS, but at the frequency band at which LIGO is interested. We need to see a signal that's 10 to the minus 19 in amplitude, so that over a kilometer scale interferometer we can measure a strain that's less than 10 to the minus 21. So that means the seismic motion needs to be attenuated by 13 orders of magnitude. To give you a sense of what that's like, it'd be like trying to hear someone breathe with a jet engine 25 meters away. You somehow need to filter out that noise, take it down 13 orders of magnitude in amplitude. So the way that's done is through a series of steps. First, on the outside of the vacuum chamber, this system in blue is the pre-isolation. There are seismometers on the ground that measure the ground motion. They feed their signals forward to linear actuators that can move this top blue stage in 6 degrees of freedom to cancel out ground motion, much the way that your noise-canceling headphones can cancel out background sounds. And that provides a very nice and quiet platform from which to build your interferometer on top of. But that's not enough. We have a system of spring and masses. So you can see these copper things here are springs. On top of them are large masses. Pretty simple technology. Several people did their thesis work on designing these springs. Turns out not to be easy. They have to alternate direction because you don't want vertical motion to couple into twisting. They have to be internally damped so you don't get resonances of those springs. Pretty much everything that you see involves the over-engineering by PhD students, postdocs, and scientists working for decades to improve these technologies. So on top of this series of masses and springs, we get our top layer, which is either our optical table or the top of a 4-stage suspension system. So this is a series of pendulum, the bottom mass of which is the test mass, the mirror that will reflect our light. And to understand why this is useful in attenuating motion, I've got a pendulum here. And the idea is that if I move my suspension point to my hand slowly, the bottom mass will follow the motion of my hand. Okay, so there's no reduction in the motion of the mass through the pendulum. But if I move my hand rapidly, faster than the resonant frequency of the pendulum, you can see the mass has trouble responding. Right? And in fact, the amplitude of motion decreases as 1 over f squared as I get above the resonant frequency. So I can take a series of pendula, and I can start to get a series of isolation. And I can do other tricks, like I can do some sensing of the bottom mass or the intermediate mass and apply some control scheme that stabilizes it so that the motion of the top of the pendulum system essentially doesn't couple at all to the bottom. And that's how seismic motion is dealt with. There's the thermal noise of the test masses. This is all done at room temperature. So our optics are at room temperature. They have energy. And that energy manifests itself as motion of the optics. So if you need to measure a displacement of the test mass of 10 to the minus 19 meters, and that's 1 billion times smaller than a single atom, and all your atoms are vibrating around, how do you do it? Well, one thing you do is you average over many atoms so that the individual motion of each atom doesn't matter that much. But the other thing you do is you arrange your optics to be a particular shape, much like Joseph Weber's bar, so that the energy that they do have concentrates itself at a particular frequency at which they resonate and ring. And as long as those frequencies are outside of the measurement band of interest, they don't affect your measurement. Now the laser is another potential source of noise. Lasers have amplitude that fluctuates and a phase that fluctuates in time. So if you were to just measure the output power of your laser, it wouldn't be constant. So you would expect that your photodetector would not see a constant signal. And of course the way to deal with that is lots of scientists, lots of physicists, lots of PhD students working for decades to improve the situation. So there's a very stable but low power laser that's used to injection lock a much higher power laser. And so you get the frequency stability of the small laser imposed on the larger laser. That larger laser is filtered through cavities before it's injected into the interferometer. And by having a high laser power, you reduce the relative importance of these fluctuations. The photodetector, of course, though, as you go to higher laser power, you might be concerned about it saturating. So a typical photodetector can handle milliwatts of power, and here we have a laser that's putting out 20 watts. So we would expect to just basically melt our photodetector. But as long as you arrange the interference conditions such that the photodetector is at a point where there's destructive interference in the absence of a gravitational wave, then that's not an issue. You're not putting power onto the detector. Turns out there's some non-technical challenges as well. Louisiana had alligators. They have logging a few miles away from the site. And so in the initial LIGO science run, it was 6 years ago, the interferometer could not operate while they were logging. They had to operate it at night. And this was a problem. So some of the upgrades that were planned for a future detector that would help isolate the ground motion from the instrument were actually implemented early. This active seismic cancellation by measuring with seismometers on the ground and then having an active platform that stabilized that was implemented partway through the initial LIGO run to allow the interferometer to operate 24 hours a day. There's a hunting range nearby. And there was concern that some people enjoying themselves in the forest shooting bullets might pierce the world's largest high vacuum chamber. And this is a $300 million facility. So you don't want that. So the solution was to put a concrete barrier over the vacuum tube. And so this was necessary for, or thought to be necessary in Louisiana, but of course, if you're doing it at one site, you do it at the other site, you make them identical. It turns out it's only ever been necessary at the Hanford site. This is what happens when you go joyriding through the desert and you get to a hill that you can't see over. It turns out it's really hard to avoid a 4-kilometer-long building. There are other issues. The Hanford site is probably most famous as being the site where nuclear fuel was produced during the Cold War. And so the groundwater is contaminated. So there are very sophisticated models of the groundwater. And the scientists that have modeled that don't want any new sources or sinks in their models. And so you can't pump water out of the ground. Okay, so why is that a problem? Turns out a 4-kilometer-long L-shaped building with that L facing upwind in the desert collects a lot of tumbleweed. Tumbleweed is a fire hazard, and the fire marshal does not like it when your tumbleweed piles up. You need a lot of water on hand to please the fire marshal, but you can't dig for it. Right? So water needs to be trucked in and stored on site. partway through the process of doing that, they realized it was cheaper to hire people to carry away the tumbleweed. So it's now one of the largest employers in the Hanford Nuclear Reservation is carrying away tumbleweed. Tumbleweed presents other interesting problems. Here's an article in Classic and Quantum Gravity, Tumbleweeds and Airborne Gravitational Noise Sources for LIGO. So could a flying tumbleweed have enough of a gravitational pull on these test masses to disturb them at a frequency at which LIGO is aiming to be sensitive? These are some of the things that people had to think about. So the final interferometer configuration that's online and operational now looks something like this. And we can ask then, what did this interferometer see? So here is the data from both the Livingston on the bottom and the Hanford interferometer on September 14th. From 10 to the minus 18 to 10 to the minus 21. So we take out the ringing, which was a factor of 1,000 times bigger than the background, and this is what we get. And you're listening to the actual data being pumped through a speaker system. It's not modified at all, other than to have that frequency where the ringing was removed. So I've spent many nights with headphones on at the detector listening to this, and when you hear strange sounds, you need to tweak something, you need to adjust your detector, and you get used to the idea that anything that's out of the ordinary is something wrong with the detector. It's been like that for 15 years. But here's what was observed 10 seconds later.
10 seconds.
You hear like a little heartbeat?
Yeah.
It's hard to hear. The colored contour plot here is a time frequency analysis that shows as time evolves, the frequency was increasing. This is that type of chirp that's expected for a binary system in spiral. To make it a little easier for your ears to hear this, let's speed it up to a point where your ears have a little better sensitivity. So here's a zoom in on that data. We have Hanford and Livingston plotted, and what's amazing is if you take the data from Livingston and you shift it back in time by 7 milliseconds and align it to the Hanford data, you get almost a perfect match. Remember, there's a 10 millisecond transit time between the detectors. So that indicates this was a source that was in the southern sky, illuminating the detectors from above. It's a simple matter to work out the cosine of the angle and figure out at what angle the source was from. You can also take these observed signals and you can look at your models for what various mass and speed of rotation sources could give similar signals. And so this red line here and this blue line here are calculations of expected signals. Were numerically calculated on a supercomputer. And you can see they match almost perfectly to the data. In fact, if you subtract those calculated signals, this is your residual. Looks just like the noise. So you have to ask yourself, is this a signal? Could this just be some random noise that happened by chance to occur in both interferometers at the same time, within 7 milliseconds, and with the exact waveform that we expect from a gravitational wave? Okay, and this is a sort of statistical analysis that has to be done to vet these signals. Okay, and so what is done is the waveform of data from one detector is cross-correlated with the waveform of data from the other detector. And normally what you'd see if there's a signal at the same time, there'd be a point in time where they're correlated, right? And you'd see the signal in both detectors. If you shift them by more than 15 milliseconds, then there's no chance that there's an astrophysical signal in both detectors at the same time. Okay, so you can generate a fake set of data by shifting the two data sets relative to each other and look for correlations. If these happen to be random correlations, not correlated, but random noise that just happen to appear at the same time, you'd expect that by shifting the data, you should also be able to generate similar random coincidences of noise. And you can shift it by various amounts and analyze the data, and shift it by more and analyze it. And you can generate hundreds of thousands of years of fake data this way, and ask how many similar magnitude signals you see. Okay, and this black line then plots how many of those signals you would see normalized to the actual measurement observation window. And so what you find is that we're talking about there's a probability of detecting a signal as shown by this black line of something like 10 to the minus 5 or 10 to the minus 6 in the measurement window in which this was observed through just random chance. That wasn't, it was just noise in both detectors happening to produce this event. Most of these high signal-to-noise ratios, and this is signal-to-noise being plotted here, versus the probability of such an event occurring randomly. Most of the noise seen here is actually due to the signal seen in one detector correlating to random noise in the other detector. So if you remove the signal of interest, and you do the same analysis with the background, you get this purple line. And what it tells you is that you'd have to operate for 22,500 years before you're likely to see random chance correlations of noise at the same time of the same magnitude. And that says nothing of the fact that the waveform matched so perfectly the predictions of numerical relativity. So this was evidence that this was indeed a passing gravitational wave that was detected. Okay, so let's look at the parameters of the system that gave us that waveform that so perfectly matches the data. Okay, it turns out to be an inspiraling binary system. And just like the inspiraling system of Hulse-Taylor, as it propagates, as gravitational wave propagates outwards, it radiates away energy. The orbital radius decreases until eventually these two objects collide and merge into one. So if you look at the amplitude and frequency of this, what you find is that these objects had to be moving so fast to produce these signals at the point they collided. In fact, they were moving at relativistic speeds, more than half the speed of light. And the simulation tells us they were only a couple hundred kilometers apart. So what can be that close to something else so massive? Okay, we also find that the total mass here is about 70 solar masses. So we've got a ton of mass. Not a ton, we've got 70 suns of masses moving at relativistic speeds within a few hundred kilometers of each other. It can't be a neutron star. They're not massive enough. Okay? It couldn't be just random dark matter. It would be too spread out. It wouldn't be dense enough to get this close together. It could only be black holes. So here are the system parameters that fit the data. A primary black hole with a mass of about 36 solar masses, and a secondary having 29 solar masses. So about 30 solar masses each. What's 36 plus 29? 65. The final black hole mass, which is determined by that ring down after the chirp, is 62 solar masses. Why don't those add up? Lost energy due to gravitational waves. Okay? Lost 3 solar masses of energy in about a fifth of a second. For that fifth of a second, this was 10 times brighter than all the energy produced by every star in the entire universe. This is the most energetic event ever observed by humans. It occurred 1.3 billion light years away. So this occurred at a time when multi-cell organisms were just forming on the Earth. That life had to evolve to a point where someone could theorize black holes, warping of space-time, collisions, gravitational waves. We needed another 100 years to develop the technology to build it, and then to turn it on. And this was actually detected 4 days before advanced LIGO was set to begin its first observation. It was on. They were doing tests, various calibrations. It was 4 in the morning. The group in Livingston was going out to do some car tests. They were going to drive their car around, brake, drive, brake, drive, brake, and see if they could see those signals in the data to help them calibrate against traffic that would be on the highway several kilometers away. Things weren't working well. They decided just to call it a night, go home. The interferometers are still operational. Good thing. Here's how big those black holes were. Their event horizon was no more than a few hundred kilometers. Okay. You could easily drive that distance to go home tonight. But there were 62 solar masses contained within this size. It occurred somewhere in the southern sky. There are only 2 detectors operational at this point. The Virgo detector is still in the process of being brought online. Both LIGO detectors observed it. And with the annulus on the sky that the timing gives us, and the detector pattern, which limits the position on that annulus to places where the detectors are sensitive, we know it's positioned within about 600 square degrees. And this is what a supercomputer calculates it would have looked like. You see the 2 black holes. This is greatly slowed down. What looks like the motion of stars around them is actually the apparent position of the stars changing as the light passes through this warped space-time. And everything you're seeing occurred in the last 2 seconds or so. Remember, these things are moving at relativistic velocities. So what does this tell us?
So yeah, I get to come in and tell you some of the fun stuff that, the interpretation of what we've seen. Thanks for the great presentation of how this was all discovered. So I'm going to be the bandwagon person who jumps in and tells you how cool this is, because I was not involved with the project at all. But I'm going to talk a little bit more about the astrophysical side of things. And kind of a summary of what we learned from this. First of all, Einstein was right. 100 years later, his prediction of gravitational waves has been directly demonstrated. The next thing we learned is that high-mass black holes exist, and I'll talk a little bit about that. Also, that black holes can form and merge over the course of the lifetime of the universe. So that's not something that was clear before this detection occurred. And again, I'll talk about that a little bit. And there's likely more to come. There's upgrades happening, Virgo coming online, so there's a lot of fun stuff to discover in the near future. And finally, even impossible endeavors are not beyond the realm of human ingenuity. That if we join together in collaborations, there's a lot of great things that can be accomplished. So we've heard a lot about black holes, and you all probably know, have been exposed to ideas and facts about black holes. I just wanted to review some of this and start off with, before we talk about black holes, which are beyond our far beyond our normal realm of experience. So I can start with things that are more inside our realm of experience. So this is actually not a real picture. This is a simulated image of the next generation human spaceflight program. the successor to the space shuttle, what we hope that'll look like. So what you're seeing here is the ambition to escape the bonds of gravity. And the idea being that if you launch something rapidly enough, it can escape a gravitational influence of a body. So I've got here Darth Vader as my assistant. And the idea is if I throw it up into the air, throw him up into the air, he comes down a fraction of a second later. If I throw him faster, it takes longer to come down. Okay, it takes longer for gravity to pull back on it and counteract that initial motion to bring it back down to Earth. And then faster and faster, starts hitting the ceiling. Hopefully he won't get angry because that's the path to the dark side. But you can imagine if I threw him fast enough, he never comes back. The time to come back gets longer and longer, and at some point it becomes infinite, and what you say is escape the gravity of the Earth. So that's the idea with spaceflight, is to escape the gravity of the Earth, and the escape speed for the Earth, a lot of you have probably heard this before, is 25, this is going slowly because this is going to be slow relative to some things later, 25,000 miles per hour, roughly. You can get off the Earth. Now imagine that you're considering the sun. Now the Earth is bound by the sun. It's drawn by its gravity and pulled around in a circle. And the Earth goes at about, I think it's 70,000 miles an hour, a bit faster. And not that much faster considering the sun is massive because the Earth is pretty far away. If you get close to the surface of the sun, you're now much closer to the source of the gravity, and the escape speed is much higher. So if you're right at the surface of the sun, your escape speed is now over 1 million miles an hour. Very hard to get away from the sun with any spacecraft, for example, if you could get that close. Now let's take a mental model of the sun, and imagine you took the sun and you squashed it down to a size of 4 miles in diameter. Don't try this in your backyard experiment. What would happen is as you're getting closer to the center of the sun, all the mass is crammed down to this 4-mile region, and you're close to that gravity. It means the escape velocity has gone up so much, it's now 700 million miles an hour, which is the speed of light. So what that means is at this point, light, which is the fastest thing in the universe, can just barely get out. So if you go squash a little bit more, then even light can't get out. And the only way you see the sun, this beautiful sunshine, is that you're seeing the light come out. If you don't see that light come out anymore, then you have what you call a black hole. So this is just a schematic of it. Actually, if a black hole is in front of a star field, as we saw earlier, you'd see a gravitational lensing effect. You'd see some distortions there, but this is a little more simple than that. So, well, what would happen if the sun turned into a black hole suddenly? Anybody have any thoughts on that? We'd all what? Oh. So here is a little animation to show you. Here's planets going around the sun. Now let's just imagine some giant hand were to squeeze the sun into a black hole. And there it goes. Now you don't see the light anymore, but the planets, they just keep on going. And that's because according to Newtonian gravity, which is a pretty good approximation to reality, the gravity only depends on two things. You saw the force law at the beginning, which is the masses of the objects involved and the distance between them. So that force law doesn't care anything about the fact that the sun is a big giant gas ball or it's squeezed down to a little black hole, or a small black hole is still the same mass. The mass hasn't changed, the distance hasn't changed, so nothing's changed as far as the motions occur. Now what has changed is that we don't have heat and light from the sun anymore, so we don't have to worry about global warming. So the bottom line is black holes don't suck. Just sort of a perception people have is that you've got this big, really strong gravitational field. It must mean that it pulls everything in. Well, the answer is it's no different from anything else with the same mass. Which all masses do suck in a sense, which they pull things toward them. But usually you have enough angular momentum or sideways motion that you don't fall in. It'll pull you towards it. If you're out in space in your rocket ship, if you're going anywhere near that gravitating body, you'll just kind of fly on by because you've got enough momentum to carry you around. If you remember the movie Interstellar, I hope I don't give this away too badly, but one of the characters goes into a black hole and he has to point the spaceship at the black hole and go straight in. You have to get into a black hole on purpose. It's not going to happen by accident because black holes don't suck. Now I say usually because there's kind of some exceptions. And I'll talk about that. So one of the things I say, this is all kind of setting the stage for this great discovery that just happened, is how do we know black holes exist before this announcement. So here's an example of how we know they exist. Because you can't see them directly, or at least we're not close to any of them where you can see this effect. This is a binary system where there's a black hole and a giant blue star going around it. And so we can see two things. One is we can't see the black hole directly, but we can see the light from that blue star, and we can see that it's moving, and it's moving around something that basically isn't there, which has a large mass. So that's one line of evidence for a black hole. By the way, the system is called Cygnus X3, so this is a real simulation of a real system. If we were close enough, we could see that, but this is an artist's conception. But so the first thing we can see is the motion of that blue star. The second thing is we can see X-rays coming out from something nearby, which is interpreted as gas falling into the black hole, heating up to really high temperatures, millions of degrees, and forming X-ray photons that come out. And that's one of these exceptions to the rule I call black holes don't suck. And it's a secondary effect. So I'm just going to illustrate how that happens here. So what's Newton's first law of motion? Anybody know? Yeah. Objects that are at rest stay at rest. So I'm staying at rest. And objects in motion stay in motion. So I'm going to go in motion. Am I going to stay in motion? Why not? Yeah, friction. So I'll go a little bit. And eventually it slows down and stops, I hope, before I hit the wall or somebody. So eventually it stops because I didn't give it too much speed. But that is, we're violating Newton's first law, apparently, just because there is an extra force there, which is a frictional force, which is slowing me down. So that's what happens. Normally, the gas going around that black hole would just go on forever, just like the planets go around the sun. But there's friction between gas particles, which slows it down and allows it to lose that speed and eventually fall into the black hole. And then as it does, the friction heats everything up, and you can see an X-ray emission. So then the gas eventually gets into the black hole. So here's another example of a black hole that we know about. This is a simulation of the center of our Milky Way galaxy. And what we've discovered is that there's an object there with about 4 million times the mass of the sun. And the way we know that is we can see, and this happens over the span of years, about 10 years, you can watch individual stars going around the sun, this hidden object, just like planets go around our sun. Here you've got whole suns going around some missing object. So you infer that there's a mass there, which is incredibly massive, and this is called a supermassive black hole, which we now understand that all giant galaxies have a supermassive black hole at the center. And that red thing is a gas cloud that's been going around too. It's another interesting object. So we see there's sort of two realms of black holes that have been detected in the universe. One is we call the stellar mass black holes, which is the first video I showed, like the size of an individual star. The others are these supermassive black holes. So that raises the question of, well, where did these black holes come from in the first place? And those two different types of black holes have two different answers. And I'll say we know where the first type comes from, and the second type is still a mystery. So here we have a star. What is a star? It's a giant ball of hot gas. But more than that, it's a representation of a balance in the force between the force that's pulling inward, called that the dark side, and the light side, which is the light pushing outward, or the thermal energy pushing outwards. And that energy comes from a nuclear power reactor at the center of the star, which is pushing outwards. So the gravity wants to pull it together, form a black hole if it could, but the nuclear power resists and keeps it balanced outwards. And so for a star like our sun, that whole balancing act lasts for 10 billion years, and in the meantime, it's a nice energy source for us to live and thrive. So that's what a star is, but what happens, like any car engine, the nuclear engine in a star is going to run out of fuel someday. So what happens when the fuel runs out? Well, you lose this push outwards, and then gravity starts pulling inwards. Now, for most stars, there's sort of a whole series of events that happens. Our sun, sun's not going to turn into a black hole. We expect it turns into a red giant, a white dwarf, and kind of slowly dies out. So that's another story. But for very massive stars, there's another thing that happens. I'm going to show a picture of that, or a movie of that. Again, an artist's conception. As the material falls in, it creates a great explosion, and at the center, the material at the center has collapsed down to a dense enough air volume to form a black hole at the center. And you're left with what we call a stellar mass black hole. There it is, the light just winked out because it's gotten so dense. And you're left with these stellar mass black holes, roughly stellar mass, roughly the mass of the sun, usually a bit more massive than the sun. So that's pretty well understood where those come from. Supernovas, exploding stars that sometimes create black holes. So now the question is, what have we learned that's new? Now, this was all the backstory. This is all what we knew up until a few weeks ago. With this new gravitational wave detection, what have we learned that's new? So a couple things I'll mention. One is that, as far as I know, this is a record-breaking black hole system. For example, the image I showed of the black hole binary in the Milky Way, these things get up to about 10 or 15 times the mass of the sun. It'd be the most massive. Now this pushes it up to several times more massive. You've got more massive black holes, as far as I know, have been detected before without getting into the realm of the ones at the center of the galaxies. So I call these extra large black holes. So that's interesting because we have a pretty clear picture of where these black holes come from. They come from stars, and we have an idea of how you map the mass of the star to the mass of the black hole. It comes from the mass at the center of the star that's able to collapse. Well, what happens is stars today in our Milky Way are full of grit. They're not the first generation of stars. There's been many generations before them. And those stars have produced grit, we call it dust, and heavy elements that have contaminated to a small degree the gas in the stars. And what that means is that the stars become like engines that are not able to run at full efficiency in terms of being able to retain their mass. So what happens is that instead of all the light coming out in a very pure star, some of the star itself kind of comes off, is dragged along with the light because of the grit that's in there that's dragging on the light effectively, and the light pushes out the material we call stellar wind. So this image here is a picture of the winds coming out of a massive star, and this is an idea of a progenitor of this gravitational wave event. Here you've got two massive stars. One of them has already gone supernova and formed a black hole, and then it's got this accretion disk, you see, like I discussed before, of material coming off and landing there and spiraling into the black hole, but you've also got the stellar wind coming out, which will reduce the mass of the star that's left over to form a black hole. And that's what sets this upper limit of 10 to 15 solar masses. Now what's interesting is that people had predicted that if you had some of the more pure stars, then you have less of this effect of the winds coming out, reducing the mass, and you could have a more massive black hole that's left behind. So that's what we think is the most likely explanation for these massive black holes, that you have what's called a pure burning star, and the technical word is a metal poor star, low metallicity star, about a tenth the amount of heavy elements that's in the sun, and that's been able to leave massive black holes behind. I say two of these pure stars form massive black holes. Why are they there? One possibility is that these were very ancient stars and ancient black holes actually that formed at very early times in the universe before these extra generations of stars could form the impurities. The other possibility, they're more in what we call low density environments, more isolated environments where there aren't so many impurities. They're formed in a dwarf galaxy is the concept here. So that's one of the things we've learned, is that these kind of black holes can exist and probably form in these metal poor stars. The other thing, now this is more controversial, so every time there's a discovery, there's usually follow-up discoveries that sometimes surprising things. So one of the possible surprises is that there is NASA has a gamma ray observatory called Fermi, which detected a flash of gamma rays at very shortly after this gravitational wave signal. And my understanding this is controversial to know, I'm not in the inside loop, so Peter probably knows and can't say, or possibly knows and can't say, I don't know. But It's not clear if this is associated or not, but if it is associated, it's very interesting because basically we don't expect to see any electromagnetic waves from a black hole binary merger like this, that it's completely dark merger. The only thing you can detect is the gravitational waves. The only way you see a flash of electromagnetic radiation, like gamma rays, is if there's some other material around there that kind of picks up on the energy and produces gamma ray burst that we could see. And one of the ideas, just to throw out, to whet your appetite, there's lots of speculation anytime something like this happens. Claim is out there. One possibility is that these black holes were actually not the product of a binary star system, but it was a single star that was rotating so rapidly it's almost ready to break apart from its own rotation. And as it collapsed, that it formed two black holes in the center of it, which then merged. And what that meant is that there was some material still around it which could form a gamma ray burst. So that's kind of exciting. But right now it's fairly speculative. We don't know what really is going on there. And of course, as the more the detectors come online of gravitational waves, we'll be able to localize things better and verify where these things are coming from. So at the beginning, we heard a quote that looking deep into nature, you'll understand everything better. So a follow-up quote from Einstein is from David Blair, one of the researchers on the gravitational wave experiments. The universe has spoken and we have understood. So it's this great sense of being able to listen to the universe in greater detail and to hear answers about what's out there. And to understand that this is only the beginning of the story. We're seeing the opening of a new window into the universe. Stay tuned. We're going to hear about lots more great discoveries, we hope, in the future. So at that point, we'll open it up to questions. Aaron?
Hi, I have two questions. First, how does rain drop off with distance from the source?
It drops off linearly with distance. So most observations that you might do, electromagnetic for instance, you're detecting power, and power scales as 1 over distance squared. So you'd expect if you go twice as far out to see a signal that's 1/4 as large. But because we're actually looking at the amplitude, not the energy in the gravitational waves, it scales inversely proportional. So if you go twice as far, the signal's half as big.
The other question is the signatures of the black holes going into each other. Are we sort of seeing that in real time, or is the frequency stretched from the original event?
There was a redshift of 0.09. So it was slightly stretched, but it was very similar to what we saw.
Cool, thanks.
In the back?
So, knowing how long you've been trying to detect these and you found one, can you say anything about how frequent you think you're going to be able to detect these?
No. It was very good news that it was detected so soon in the observation run.
Well, if Dr. Borowski mentioned that there was a possibility it could be based on those stars that are pure burners, can we do some sort of statistical analysis, like how many pure burners were there at that point in time? Any burners there?
Well, from what I've seen, just you can connect this single observation to statistical predictions from astrophysical sources like these binaries. And so if you have a model that will predict this event happening so quickly, I think the prediction is that there'll be more of them detected, possibly just below, slightly below the level of what we've seen. So I would expect as the sensitivity goes up, you start seeing more of them, but I don't know the actual numbers. Right here in the middle?
So if it was happening during the formation of the black hole, does the light traveling along the gravitational wave affect the time it would take to get here? Like the gravitational wave spike, and if the light is traveling with it, would it slow down further or?
So I'll speak to that. One thing that's nice about gravitational waves as a tool of observation is that they interact so weakly with matter. Of course, that's what makes them so difficult to detect as well. But the fact that gravitational waves interact so weakly with matter means they're not scattered or obscured by interstellar dust or even the gravitational waves from the Big Bang could potentially be detected even though there was no light present at the time of the Big Bang. So it would potentially allow us to see even further back. That also means that there's very little dispersion. You wouldn't expect it to travel at a speed that's retarded because of the material it's passing through or such.
Well, I mean, with the light.
The light would likely be delayed. It's got dust to propagate through, and that produces an index of refraction that slows it down. Which is why these optical observatories are doing follow-up observations. So after the detection of a gravitational wave, it triggers an alert to a network of observatories that then train their telescopes on the area of the sky that the gravitational wave observatories localize the source to. And the hope is that within the first 24 hours or so, that they'd be able to observe some optical effects that would come along with this. You'd expect that much more if it was like a neutron-star in spiral, where there's actually matter to produce light. With these black hole systems, there's no actual matter in the black holes. It's pure energy. So it's much harder to imagine optical sources coming out of that.
I have another question. I guess I was wondering, you said that it was detected on September 14th. Like, why are we just hearing about it?
So in order to publish a result that you have confidence in, there's a lot of detector characterization that needs to be done to verify that it wasn't some spurious effect. There's a lot of things you could imagine could produce something that looked like a signal. Could be some magnetic storm, could be solar flares, could be any variety of things. And there's about 100,000 sensors that are part of the observatory that monitor environmental conditions, the state of the interferometer, things other than the main gravitational wave signal. Those all need to be checked to vet them, make sure that there were no abnormal effects going on in the environment that might contribute to this.
I was just trying to imagine, like I know when you look through the telescope, is a computer or something takes an image and you see it with your eyes, but was there a computer that recognized it and sent a text message to someone?
That is exactly what happened. So it took about 3 minutes. This is Marco Drago. He was that postdoc in Germany. I was middle of the night here, but in Germany people were working, and he got a message that said there's some abnormally large signal in the gravitational wave detector. It took about 3 minutes for the computer to figure that out and alert him. And then within 5 minutes of that, the entire collaboration knew. Another thing that I should point out is that normally during observation runs, there's a group of people who are part of this collaboration whose job it is to try to trick the other scientists by injecting a signal into the interferometer that looks like a gravitational wave to test their ability to find it. Okay? It turns out because the observation run hadn't started yet, that blind injection group was not yet operational and online. So while normally there'd be many months before the information was revealed as to whether or not it was a blind injection or not, in this particular case, because of the timing, the collaboration pretty much knew that there was something interesting going on that wasn't one of these blind injections. Aaron?
Have there been a lot more events since then that they just haven't verified yet?
I'd say there are interesting things being looked at. But there have been lots of false alarms in the past, right, on big events. And so with a collaboration this size and an event of this significance, it's really important to vet it, make sure it's gone through all the vetting process, the peer review process, before it's published and publicized. And that takes time. Yes?
Speaking of the false alarms that happened, when there was before advanced LIGO, I remember reading up a little bit about how there was a particular event that was saw as like, oh, this is gravitational waves. You guys came out in public about it and they discovered there was a mistake. What was going to be the issue with that?
I don't think there was any coming out in public about that.
Oh, no.
No.
Okay.
I was at the meeting where they opened the envelope to see if there was a blind injection, and there was. And it was very secretive. It was called Big Dog because the localization in the sky had it near Canis Major, the Big Dog. And so it was 3 or 4 months of discussion and detector characterization and analysis of all these signals. The only information that the collaboration didn't have was whether the signal had been injected by the injection group. So that was the last thing we found out. There were literally waitresses with champagne bottles standing around when they opened the envelope and discovered that it was a blind injection. Sean?
Did you get the drip of champagne anyway?
We did.
Are there more facilities being built? Would that be advantageous?
Are there more facilities being built? Yes, there are. So there are several. I can show you a mock-up of the Kagra site in Japan. I worked on the prototype for this interferometer for about 4 years in Tokyo. Tokyo is a terrible place to build a gravitational wave detector. There's far too much noise. But we learned how to do it, how to operate. And the intent then was to move into the Kamioka mines, which are far underground and in an isolated location. And this is a 3-kilometer, so similar scale to LIGO. It's actually going to operate with cryogenic mirrors. So in many ways, it's a more advanced detector, but it's also a few years behind where LIGO is. The Virgo detector is coming online in the next few months, hopefully. And then the other thing that's interesting is when these detectors were first conceived of, the thought was that it'd be really difficult to be able to tell a gravitational wave signal from other noise sources that might shake your mirrors. And so a decision was made to build 2 interferometers in the LIGO beam tube at Hanford, Washington. One was 4 kilometers long, one was 2 kilometers long. And the thought was that if you're measuring a strain, you should see twice the amplitude of the signal in the 4-kilometer detector that you see in the 2-kilometer detector. And it sounds very good when you're talking about detection. But somewhere close to $1 billion of money spent, the National Science Foundation decided that really we should be focused on observation and learning information about the universe from these detections rather than just saying, oh, look, we saw something. So a study was done, and we found that with this detector pattern, this ability to localize in the sky, there's a lot of uncertainty along this the plane of the triangle formed by the Hanford. You see this is labeled HHLV, the Hanford, the other Hanford, the Livingston, and the Virgo detectors. That second Hanford interferometer is giving you no extra information to localize the source. So a decision was made to pack up the optics that were part of that detector, store them, so that one day they could be deployed in India. So if funding allows it, and you could build an observatory in India, we already have an interferometer available to go there, and you could greatly improve the localization in the sky. Last week, that was approved. It's amazing what a little good news will do to grease the wallets of the people who are funding these things.
And there's space ones coming, right?
And there's space-based detectors as well. Those are significantly different in that they'll operate at much lower frequencies, so they won't have any. They won't see the same sources that the ground-based detectors will see. But again, those are things that need additional funding. And honestly, it's unclear in today's environment whether a project like this could be funded. This was a line item in Congress's budget for about 25 years. It was that big of an expense. It was the largest expense that the National Science Foundation had ever spent on a project. And it's probably worth noting that last week, Lamar Smith, the chair of the Senate Science Committee, put forth a resolution that would require, I guess they approved a resolution that would require that any expenses by the National Science Foundation be justifiable in terms of the national interests of the United States. So it's hard to believe that a project like this could be funded today because of the political environment. I don't think that makes it any less significant of a discovery or any less of a value for the money that the taxpayers spent.
If you're trying to do this word that we heard regarding the noise or the signal or the sound, it's called a chirp. What would you call it?
I'd call it a chirp.
Okay,
But maybe that's because people have always been telling me it's a chirp.
okay. Thank you very much.
I have an interesting example of some of the other sources
Yes.
that we might potentially observe
Yes.
someday.
Oh, we'll see.
I'll let this play in the background, but I'll point out those audio waveforms are things that I made about 15 years ago. You heard the chirp in there.
Yes.
There were some other sounds you heard. There was sort of a staticky background. That's meant to represent the stochastic background from the Big Bang, sort of a white noise. It's very difficult to detect because you don't have a waveform to look for. It's basically white noise. But the models say it should be there, and if we were sensitive enough, we could see it. The other thing that you might have heard was sort of a ringing, a constant frequency ringing that was slightly modulated. This would be the sound of a spinning neutron star that has some asymmetry to its mass distribution. So think of a mountain on a neutron star as it spins, would be generating a periodic gravitational waveform. Those are really nice in that if you detect something like that, it's stable over many years. So even if you only had a single detector detecting it, you could integrate over many years, and your detector moves around the Earth and around the Sun. So your effective ability to localize this, it's as if you had a ring network of detectors.
Do you expect the same sound? Is
I-
that an expectation out of that, or do you think?
Well-
No, of course, just speculating.
So you hear the chirp, but you also hear that ringing.
Okay, yeah,
Yep. That's what you'd expect for a spinning neutron star.
is that high sound?
That high frequency sound.
That's what you call the chirp right there, that high frequency?
No, the chirp was the changing frequency in
Oh,
time.
okay, thank you
And that's what you get from the binary star in spiral, or the binary black hole in spiral.
very much.
Yes, right
So
here.
what is the idea of the energy that was given off by the combination of the black hole? Because you said it's not giving off any electromagnetic radiation, so what do they assume that energy form is given off as?
Gravitational radiation. So that was coupled into space-time directly.
Okay.
We take one more question. Maria, did you have one more question?
You know, like when we take the classes in field theory and stuff, so light is propagated by photons. Does this observation reveal anything about gravitons, or like did they say, was that gravitational wave propagating at speed of light?
So the question was, does this observation reveal anything about gravitons? I haven't heard that said. What I have heard is that if gravity is transmitted through gravitons, that this corresponded to, I think it was 10 to the 88 gravitons being emitted during that final chirp. Okay, well, thank you for coming and being interested in this.